The headlines scream about an interstellar comet named 3I Atlas that supposedly passed through our solar system in late 2025. Scientists debate whether this ancient visitor from beyond our neighbourhood could somehow influence our sun's behaviour. But while astronomers argue about cosmic visitors and their potential effects, something far more immediate and terrifying happened that barely made the news. Between November 9th and November 13th, 2025, our star unleashed a barrage of energy that should have every person on Earth paying attention. 3 massive solar flares erupted in rapid succession, an X1.7 on November 9th, an X1.2 on November 10th, then on November 11th, an absolutely monstrous X5.1 flare that released more energy in minutes than humanity has consumed in its entire existence. Each explosion hurled billions of tons of charged particles toward Earth at speeds approaching 2 million kilometers per hour. The resulting geomagnetic storms reached G4 severity levels, the second highest alert category possible. This wasn't a theoretical discussion in academic journals. Radio communications across Africa and Europe vanished without warning. Power grid operators in South Africa received urgent bulletins from their National Space Agency, warning of dangerous currents that could induce catastrophic failures in transformers. Satellite companies scrambled to protect their hardware. Airlines rerouted polar flights to protect passengers and crew from radiation exposure. This was infrastructure under attack from our own star. Yet most people have no idea how close we came to experiencing something that could have changed everything. Modern civilization runs on electricity, satellite communications, and GPS navigation. All of these systems have critical vulnerabilities to space weather events. A severe enough geomagnetic storm could trigger cascading failures across power grids, disable satellite constellations, and knock out communication networks for weeks or months. The Carrington event of 1859 offers a glimpse of what's possible. That historic solar storm was so powerful it caused telegraph wires to spark and set fires. Telegraph operators received electric shocks. The aurora borealis appeared as far south as the Caribbean. But in 1859, human technology was primitive compared to today. We had telegraph wires, not internet cables, oil lamps, not power grids serving millions of people, sailing ships, not satellite-guided aircraft carrying hundreds of passengers. If an event like Carrington happened today, the consequences would be catastrophic. The National Academy of Sciences estimated that a severe geomagnetic storm could cause up to $2 trillion in damage to the United States alone. Recovery could take 4 to 10 years. That's not speculation. That's analysis based on known vulnerabilities in our electrical infrastructure. The November 2025 events didn't reach Carrington levels, but they came close enough to demonstrate how exposed we are. G4 storms represent the threshold where localized voltage control problems begin appearing in power systems. Transformer damage becomes possible, satellite operations get disrupted, and these storms sustain their intensity for days, not hours, because multiple coronal mass ejections overlapped and reinforced each other. Power grid operators understand this threat, but the public remains largely unaware. When your lights flicker during a thunderstorm, you know exactly what's happening. When space weather causes similar problems, the connection isn't obvious. The enemy is invisible, operating through electromagnetic fields you can't see or feel directly. The physics behind these events reveals just how vulnerable we've become. When charged particles from the sun interact with Earth's magnetic field, they induce electric currents in long conducting paths. Power transmission lines act like antennas, picking up these geomagnetically induced currents and channeling them into transformers that were never designed to handle them. High-voltage transformers are particularly susceptible because they operate at the edge of their design limits under normal conditions, add unexpected DC currents during a geomagnetic storm, and they can overheat, saturate, or fail catastrophically. What makes this even more concerning is the global nature of transformer manufacturing. These aren't components you can order from a warehouse. Each high-voltage transformer is custom-built, weighing hundreds of tons, requiring specialized transportation and installation. Manufacturing lead times stretch months or years. If a severe space weather event damaged dozens of transformers across a region, replacement could take years, not weeks. The November storms also highlighted vulnerabilities in satellite infrastructure that most people take for granted. GPS satellites experienced increased radiation exposure. communication satellites had to be placed in protective modes. The drag from expanded atmospheric heating during the storm accelerated orbital decay for low Earth orbit satellites, requiring additional fuel consumption to maintain proper altitude. Consider how dependent modern life has become on satellite services. GPS doesn't just help you navigate to the grocery store, it synchronizes cell phone networks, enables precision agriculture, guides emergency responders, and provides timing signals for financial transactions. Lose GPS for an extended period, and the economic disruption cascades through multiple sectors simultaneously. The timing of the November events carries additional significance, because they occurred during what was supposed to be a moderate solar cycle. Solar cycle 25 began around 2019, with predictions suggesting it would produce relatively mild activity compared to historical averages. Instead, November alone witnessed 6 X-class flares, many originating from the same active region. That's not moderate behavior, that's explosive activity that exceeded forecasting models. This discrepancy between predictions and reality exposes a fundamental limitation in our understanding of solar physics. We can observe the sun continuously with sophisticated instruments. We can model magnetic field evolution with supercomputers. We can track active regions as they rotate across the solar disk. But we still can't predict with high confidence when a particular region will erupt or how powerful that eruption will be. The challenge becomes even more complex when you consider that solar activity doesn't operate in isolation. The sun exists within a dynamic environment where interplanetary magnetic fields, solar wind conditions, and even interactions with objects passing through the inner solar system might influence when and how energy releases occur. The traditional view treats the sun as a self-contained system driven entirely by internal processes. But recent observations suggest the reality might be more interconnected than we previously understood. This interconnectedness means that space weather forecasting remains an inexact science, despite decades of research and billions of dollars in monitoring infrastructure. We can detect solar flares within minutes of their occurrence. We can track coronal mass ejections as they propagate through space. We can issue warnings hours or days before geomagnetic storms impact Earth. But we can't predict with certainty when the next major event will occur or how severe it will be. The November 2025 sequence demonstrated both the capabilities and limitations of current space weather forecasting. NOAA's Space Weather Prediction Center successfully issued G-force storm warnings based on observed coronal mass ejection characteristics and propagation models. Grid operators and satellite companies received advance notice and took protective measures. The system worked as designed for providing tactical warning of incoming disturbances, but strategic forecasting remains elusive. Nobody predicted that active region 4274 would produce 3 major flares in 5 days. Nobody anticipated the storm train effect, where multiple coronal mass ejections would merge and amplify each other. These were reactive responses to events already in progress, not proactive predictions that could enable long-term planning and preparation. The gap between tactical and strategic forecasting capabilities has profound implications for infrastructure planning and risk management. Utilities can respond to storm warnings by adjusting grid operations and monitoring transformer temperatures more closely. But they can't plan maintenance schedules, spare parts inventory, or system upgrades based on accurate predictions of when severe events will occur months or years in advance. This uncertainty creates a challenging policy environment. How much should society invest in hardening infrastructure against rare but catastrophic events? How do you justify spending billions on protection against something that might not happen for decades? How do you maintain public support for preparedness when the threat remains largely invisible until it materializes? The November events also revealed concerning trends in the vulnerability of modern technology. Our increasing dependence on satellite services, GPS navigation, and networked systems creates new pathways for space weather impacts to propagate through society. A power outage that might have been a minor inconvenience 30 years ago can now disrupt supply chains, financial systems, and communication networks in ways that compound the original damage. The proliferation of low Earth orbit satellite constellations adds another layer of complexity. Companies like SpaceX, Amazon, and others are launching thousands of satellites to provide global internet coverage. These satellites operate at altitudes where atmospheric drag during geomagnetic storms becomes significant. The February 2022 loss of 40 Starlink satellites due to increased atmospheric density during a relatively minor storm, provides a preview of what could happen during a major event. As we look toward the remainder of solar cycle 25, which is expected to peak sometime in 2025 or 2026, the November events serve as both warning and preview. If the Sun can produce this level of activity during what should be a moderate cycle, what might happen during the actual solar maximum? What if multiple active regions become unstable simultaneously? What if the next storm train involves even faster coronal mass ejections or better Earth-directed geometry? These aren't hypothetical concerns. They're scenarios that space weather researchers actively study and that emergency planners increasingly incorporate into their assessments. The question isn't whether another severe space weather event will occur. The question is when, and whether we'll be ready when it does. It does. The infrastructure implications extend far beyond power grids and satellites. Modern supply chains depend on just-in-time delivery systems coordinated through GPS and satellite communications. A prolonged disruption could trigger shortages of everything from medical supplies to food. Manufacturing facilities rely on precise timing signals for automation. Financial markets require nanosecond synchronization for high-frequency trading. These interconnected systems create a web of vulnerabilities that few people recognize. Consider the cascade effects that could follow a Carrington-level event today. Hospitals lose power and backup generators fail due to transformer damage. Cell towers go dark because their backup batteries drain within hours. Internet routing becomes chaotic as GPS timing fails. Credit card transactions stop processing. ATMs shut down. Gas stations can't pump fuel because their electronic payment systems are offline. Within days, the economic disruption spreads through every sector of society. The psychological impact would be equally devastating. A population accustomed to instant communication and constant connectivity would suddenly find themselves isolated. Social media platforms would go silent. News organizations couldn't broadcast. Emergency services would struggle to coordinate responses. The social fabric that holds modern civilization together depends on electronic infrastructure that space weather can destroy in minutes. Yet despite these vulnerabilities, public awareness remains shockingly low. Surveys consistently show that most people have never heard of space weather. They don't know what a coronal mass ejection is. They can't explain how solar flares affect technology. This ignorance isn't their fault. The threat is invisible and the consequences seem abstract until they materialize. But that ignorance becomes dangerous when it prevents society from taking appropriate protective measures. The economic argument for space weather preparedness is overwhelming. The cost of hardening critical infrastructure represents a fraction of the potential damage from a severe event. Installing surge protectors on power transformers costs thousands of dollars per unit. Building redundant communication systems requires modest investments. Creating stockpiles of replacement components involves manageable expense. Compare those costs to the trillions in damage that a Carrington-level storm could inflict. Military planners understand this arithmetic. The Department of Defense has invested heavily in space weather monitoring and hardened communication systems. They recognize that national security depends on maintaining command and control capabilities during solar storms. But civilian infrastructure remains largely unprotected because the incentive structures don't align. Private companies focus on short-term profits. Regulatory agencies move slowly. Politicians respond to immediate crises rather than future threats. The insurance industry is beginning to wake up to space weather risks. Lloyd's of London issued reports warning that satellite insurance claims could reach billions of dollars during a severe solar storm. Some insurers now exclude space weather coverage from certain policies. Others are developing new risk models that account for coronal mass ejection probabilities. Market forces may eventually drive protective investments that government regulation hasn't achieved. International cooperation on space weather presents both opportunities and challenges. Solar storms affect the entire day side of Earth simultaneously. Geomagnetic disturbances compress magnetospheres globally. No single nation can address these risks in isolation. Data sharing agreements between space agencies help improve forecasting. Joint research programs advance scientific understanding. But political tensions complicate coordination when it's needed most. The European Space Agency operates several spacecraft that monitor solar activity from different vantage points. Japan contributes advanced magnetometer networks. China launches solar observation missions. When these assets work together, They provide comprehensive coverage of space weather conditions. But during international crises, cooperation can break down precisely when accurate forecasting becomes most critical for preventing conflicts from escalating. Climate change adds another dimension to space weather concerns. As global temperatures rise, power grids face increasing stress from extreme heat events. Air conditioning demand spikes during heat waves, pushing electrical systems to their limits. If a severe geomagnetic storm coincided with a summer heat dome, the combined stress could trigger widespread blackouts that would be difficult to restore quickly. The intersection of terrestrial and space weather creates compound risks that emergency planners are only beginning to understand. Urban heat islands make cities particularly vulnerable to this combination of stresses. Concrete and asphalt absorb solar radiation during the day and release it at night, keeping temperatures elevated. Power demand for cooling remains high even after sunset. If space weather damaged transformers during a heat wave, restoring power would become a race against time to prevent heat-related casualties. The aging electrical grid in many developed countries compounds these vulnerabilities. Much of the infrastructure was built decades ago when space weather wasn't considered a design factor. Older transformers lack protective devices. Legacy control systems can't isolate problems quickly. Communication networks between grid operators rely on technologies that space weather can disrupt. Modernizing this infrastructure requires massive investments that ratepayers and politicians are reluctant to approve. Developing nations face even greater challenges. Their electrical grids are often less robust and have fewer redundancies. Replacement parts may not be readily available. Technical expertise for rapid repairs might be limited. A space weather event that causes inconvenience in wealthy countries could trigger humanitarian crises in regions with less resilient infrastructure. The global nature of space weather means that international assistance would be essential, but donor nations might be dealing with their own recovery efforts. The November 2025 events occurred during a period of relative geopolitical stability. Imagine similar solar activity during a major international crisis. Military communication systems stressed by space weather. Satellite reconnaissance capabilities degraded. GPS navigation unreliable for precision weapons. The fog of war would thicken considerably, increasing risks of miscalculation and escalation. Space weather doesn't pause for human conflicts. Commercial aviation faces unique exposure to space weather risks. Flights over polar regions receive higher radiation doses during solar storms because Earth's magnetic field provides less protection at high latitudes. Airlines must balance passenger safety against economic pressures to maintain schedules. Rerouting flights to lower latitudes increases fuel costs and travel times. Cancelling flights strands passengers and disrupts global travel networks. The aviation industry has developed protocols for managing space weather, but implementation varies between carriers and regions. Space weather also affects precision agriculture systems that modern farming depends on. GPS-guided tractors enable efficient planting and harvesting. Automated irrigation systems rely on satellite communications. Weather monitoring networks depend on reliable data transmission. A disruption during critical growing seasons could reduce crop yields and increase food prices. The interconnection between space weather and food security represents another hidden vulnerability in modern civilization. The financial sector's dependence on precise timing makes it particularly susceptible to space weather disruption. High-frequency trading algorithms require nanosecond synchronization between markets. Electronic payment systems must timestamp transactions accurately. Banking networks need reliable communication links between branches and data centers. GPS provides the timing signals that keep these systems synchronized. Lose that timing reference during a solar storm, and financial markets could experience chaos that makes previous crashes seem orderly. Research into space weather impacts continues advancing, but significant gaps remain in our understanding. The relationship between solar magnetic fields and flare production involves complex physics that challenge our best models. The interaction between coronal mass ejections and Earth's magnetosphere depends on variables that are difficult to measure in real time. Predicting which active regions will produce major eruptions remains more art than science. The emergence of artificial intelligence offers new tools for space weather forecasting. Machine learning algorithms can identify patterns in vast datasets that human analysts might miss. Neural networks trained on decades of solar observations might predict flare probabilities better than traditional physics-based models. but AI systems require extensive validation before they can be trusted for critical infrastructure protection. False alarms waste resources and erode confidence. Missed warnings can be catastrophic. The story of November 2025 isn't just about what happened, it's about what could happen next. Solar Cycle 25 continues building toward its peak. Active regions will continue emerging and evolving. Some will produce major flares. Some of those flares will be Earth-directed. The question isn't whether we'll face another severe space weather event. The question is whether we'll be ready when it arrives. The Sun has issued its warning. The infrastructure stress tests are complete. The vulnerabilities are documented. The economic arguments are compelling. What happens next depends on choices we make as individuals, communities, and civilizations. We can continue assuming that space weather is someone else's problem, or we can recognize that our technological civilization exists at the mercy of a variable star that doesn't care about our convenience or prosperity. The clock is ticking. The Sun won't wait for us to get ready. Every day we delay hardening our infrastructure is another day we remain vulnerable to the next great solar storm. The November events gave us a preview of what's possible. The question is whether we'll heed the warning or learn the hard way that space weather is not an abstract scientific concept, but a clear and present danger to everything we've built. The implications reach into areas most people never consider. Medical devices increasingly rely on GPS timing for synchronization. Pacemakers and insulin pumps depend on wireless networks that space weather can disrupt. Hospital backup power systems assume grid restoration within days, not months. During the November storms, some medical facilities reported intermittent communication failures with remote monitoring systems. These weren't life-threatening disruptions, but they exposed vulnerabilities that could become critical during a more severe event. Emergency response systems face cascading failures during space weather events. First responders rely on radio networks that ionospheric disturbances can render useless. GPS coordinates for ambulances and fire trucks become unreliable. Computer-aided dispatch systems lose connectivity. The very systems designed to help during disasters become part of the problem. November 2025 showed us glimpses of these failures. Radio operators across Europe reported complete loss of high-frequency communications during peak storm conditions. The psychological dimension of space weather extends beyond immediate infrastructure impacts. Modern society operates on assumptions of constant connectivity and reliable power. When those assumptions break down suddenly and without obvious cause, panic spreads faster than accurate information. Social media amplifies confusion during normal disasters. During a space weather event, social media itself becomes unreliable, leaving people isolated and afraid. Consider what happened during localized power outages in recent years. People hoarded supplies, traffic systems failed, cell towers went dark. Now multiply that response across entire regions simultaneously. Add the confusion of invisible electromagnetic forces causing problems that seem random and inexplicable. The social order that depends on electronic coordination would face unprecedented stress. Financial markets represent another critical vulnerability that November's events barely tested. Modern trading operates on microsecond timing. Algorithms execute millions of transactions per second based on tiny price differences. GPS provides the synchronization that keeps global markets coordinated. Lose that timing reference during a major solar storm, and the financial system could experience disruptions that make previous crashes seem manageable. High-frequency trading firms understand this risk better than most market participants. Some have invested in atomic clocks and other backup timing sources. Others maintain trading floors in different geographic regions to hedge against localized disruptions. But these preparations focus on brief outages, not the extended disruptions that severe space weather could cause. The insurance industry is beginning to price space weather risks into their models. Satellite operators now pay higher premiums during solar maximum periods. Some policies exclude space weather coverage entirely. Power companies face increasing scrutiny of their grid-hardening investments. But insurance can only transfer risk, not eliminate it. If claims from a Carrington-level event exceeded industry capacity, the broader economy would absorb the losses through higher prices and reduced services. Education systems also carry hidden vulnerabilities to space weather. Online learning platforms depend on satellite internet in rural areas. Student information systems require reliable data connections. Even basic classroom technologies like interactive whiteboards need network connectivity to function properly. A prolonged space weather event during the school year could disrupt education for millions of students, particularly those in areas with less robust infrastructure. The supply chain implications extend beyond immediate shortages to long-term economic restructuring. Just-in-time manufacturing assumes predictable transportation networks. Automated warehouses depend on GPS for robotic navigation. Inventory management systems require constant connectivity to optimize stock levels. A severe space weather event could force companies to rebuild supply chains with more redundancy and local sourcing, increasing costs but improving resilience. Food distribution networks face particular exposure because they operate on thin margins with minimal storage capacity. Supermarkets typically maintain only a few days of inventory. Delivery trucks rely on GPS navigation and electronic logistics systems. Cold storage facilities need reliable power to prevent spoilage. The November storms caused minor delays in some shipments, but a more severe event could trigger food shortages in urban areas within days. Water treatment and distribution systems increasingly depend on electronic controls and communication networks. Pumps require precise timing coordination. Chemical dosing systems need remote monitoring. Billing and customer service depend on database connectivity. While water infrastructure includes more manual backup systems than power grids, extended space weather disruptions could affect water quality and availability in some regions. The November 2025 events revealed concerning trends in space weather intensity that suggest future risks may be higher than historical averages indicate. Solar Cycle 25 has consistently exceeded early predictions. The magnetic complexity of active regions appears to be increasing. The speed and intensity of coronal mass ejections show more variability than previous cycles. Climate patterns in the upper atmosphere may be affecting how geomagnetic storms propagate and intensify. Satellite data from the past few decades reveals subtle changes in how Earth's magnetosphere responds to solar wind pressure. The protective magnetic bubble around our planet may be weakening slightly due to long-term variations in the magnetic field. These changes are small individually, but could combine to make future space weather events more impactful than similar storms in the past. Urban planning rarely considers space weather risks, despite cities concentrating the most vulnerable populations and infrastructure. High-rise buildings depend on elevator systems that power outages disable. Subway networks require constant electrical power for ventilation and safety systems. Traffic management relies on electronic signals and communication networks. The urban heat island effect makes cities particularly vulnerable to extended power outages during summer months. Rural areas face different but equally serious challenges during space weather events. Isolated communities depend on single power lines that are harder to repair quickly. Communication systems may have fewer backup options. Emergency services cover larger areas with limited resources. The self-sufficiency that rural communities traditionally maintained has eroded as electronic systems replace mechanical alternatives. The military implications of space weather extend beyond communication disruptions to fundamental questions of national security. Modern warfare depends on satellite reconnaissance, GPS-guided weapons, and networked command systems. A severe space weather event could blind intelligence gathering capabilities, disrupt precision strikes, and fragment military communications exactly when they're needed most. International tensions could escalate rapidly during space weather events, as normal communication channels fail and surveillance capabilities degrade. Military leaders might interpret equipment failures as enemy action. Diplomatic channels that depend on electronic communication could go silent at critical moments. The fog of war would thicken considerably when electromagnetic storms disable the sensors and networks that modern militaries depend on. Space weather also affects the growing commercial space industry in ways that could cascade back to Earth. Satellite internet constellations like Starlink provide backup connectivity for remote areas. Launch schedules depend on space weather conditions for crew safety. Space manufacturing experiments require stable orbital environments. As humanity's economic activities expand beyond Earth's atmosphere, space weather becomes an increasingly important factor in economic stability. The psychological preparation for space weather events lags far behind technological preparation. Most people have never experienced a prolonged power outage or communication blackout. The skills needed for self-sufficiency during extended outages have atrophied in urban populations. Mental health services that increasingly operate through telemedicine would be unavailable exactly when stress levels peak. Community resilience varies dramatically based on social cohesion and local preparedness. Neighbourhoods with strong social networks and emergency planning fare better during disasters. Areas with high trust levels see more cooperation and less panic. But space weather events affect large regions simultaneously, potentially overwhelming even well-prepared communities with refugees from less prepared areas. The technological solutions for space weather protection exist, but remain expensive and incompletely deployed. Power grid operators can install surge protection devices, but utilities resist investments that don't generate revenue. Satellite operators can build more radiation-hardened spacecraft, but the additional costs reduce competitiveness. Communication networks can add redundancy, but backup systems require ongoing maintenance and testing. Research continues advancing our understanding of space weather physics and improving forecasting capabilities. New spacecraft provide better monitoring of solar conditions. Computer models simulate magnetospheric dynamics with increasing accuracy. Artificial intelligence analyzes vast datasets for patterns human researchers might miss. But fundamental uncertainties remain about predicting when specific active regions will erupt and how powerful those eruptions will be. The November 2025 events demonstrated both the progress we've made in space weather science and the gaps that remain. We successfully detected the flares within minutes of occurrence. We tracked the coronal mass ejections as they propagated through space. We issued warnings that allowed protective measures to be implemented. But we couldn't predict the timing or intensity of the original eruptions, and we underestimated how the multiple storms would interact and amplify each other. International cooperation on space weather monitoring has expanded significantly over the past decade. The European Space Agency contributes advanced solar observation missions. Japan operates ground-based magnetometer networks. Multiple countries share data through coordinated space weather services, but political tensions can complicate this cooperation exactly when it's needed most for preventing conflicts during infrastructure disruptions. The economic incentives for space weather preparation remain misaligned with the risks. Companies focus on quarterly profits rather than decadal risks. Politicians respond to immediate crises rather than future threats. Individuals prioritize visible dangers over invisible electromagnetic fields. This mismatch between risk timescales and decision-making horizons creates systematic underinvestment in protection measures. Climate change interactions with space weather add another layer of complexity to risk assessment. Upper atmospheric heating during geomagnetic storms affects satellite drag and orbital decay rates. Changes in atmospheric circulation patterns may alter how space weather impacts propagate to ground level. The increasing frequency of extreme weather events on Earth's surface could coincide with space weather disruptions, creating compound disasters that exceed response capabilities. The aging workforce in critical infrastructure sectors compounds space weather vulnerabilities. Many power plant operators and grid technicians learned their skills before space weather was widely recognized as a threat. Younger engineers understand computer systems better, but may lack experience with manual backup procedures. Knowledge transfer between generations becomes critical when automated systems fail and manual intervention is required. Educational institutions have begun incorporating space weather into engineering curricula, but implementation remains uneven. Some universities offer specialized courses in heliophysics and space weather forecasting. Others barely mention electromagnetic risks in electrical engineering programs. Professional development for working engineers varies widely between employers and regions. The November storms tested emergency communication systems that many organizations assumed would remain operational during disasters. Amateur radio networks provided backup connectivity when commercial systems failed. Satellite phones offered alternatives to terrestrial networks, but these backup systems have limited capacity and require specialized knowledge to operate effectively. Public health implications of extended power outages during space weather events could be severe, particularly for vulnerable populations. Elderly residents depend on air conditioning during heat waves and heating during cold snaps. Dialysis patients require regular treatment at medical facilities. Medication that requires refrigeration spoils without reliable power. Emergency medical services struggle when communication and navigation systems fail simultaneously. The cascading effects of space weather disruptions can persist long after the original storm ends. Damaged transformers take months to replace. Satellite constellations may need years to fully recover from radiation damage. Economic disruptions ripple through supply chains for extended periods. Social trust in technological systems may erode, affecting adoption of new innovations. Transportation networks face multi-layered vulnerabilities to space weather that go beyond GPS navigation failures. Modern aircraft depend on satellite communications for oceanic flights. Air traffic control systems require precise timing synchronization. Railway signaling increasingly uses electronic systems vulnerable to electromagnetic interference. Even automotive transportation could be affected as vehicles become more computerized and connected. The November 2025 events offer a preview of challenges that will only intensify as technology becomes more sophisticated and interconnected. Artificial intelligence systems require massive computational resources that power outages disable. Internet of Things devices create millions of potential failure points. Autonomous systems from vehicles to manufacturing robots assume constant connectivity that space weather can sever. Financial sector resilience planning typically focuses on cybersecurity threats and operational disruptions, but gives less attention to space weather risks. Banking systems depend on precise timing for transaction processing. Credit card networks require satellite connectivity for authorization. Automated trading systems assume reliable market data feeds. The interconnected nature of global finance means that space weather impacts in one region can propagate worldwide through electronic networks. The insurance industry's evolving approach to space weather risks reflects growing awareness of potential losses. Some policies now explicitly exclude space weather coverage. Others offer specialized protection for satellite operators and utilities. Risk modeling incorporates space weather scenarios into catastrophe planning. But the industry's capacity to handle claims from a truly severe event remains questionable. Corporate business continuity planning increasingly includes space weather scenarios, though implementation quality varies widely. Technology companies tend to have more robust backup systems and disaster recovery procedures. Manufacturing firms may lack adequate protection for automated production lines. Service industries often assume that communication networks will remain operational during emergencies. The human factor in space weather response deserves more attention than it typically receives. Operators managing critical systems during storms face high stress levels and information overload. Decision-making degrades when multiple alarms sound simultaneously. Training for space weather scenarios remains limited compared to other emergency types. The November events highlighted cases where human error compounded technical failures. Community preparedness for space weather lags behind preparedness for other natural disasters. Most emergency management agencies focus on hurricanes, earthquakes, and floods rather than electromagnetic storms. Public education about space weather remains minimal. Emergency supply recommendations rarely consider extended power outages lasting weeks or months. The global nature of space weather risks requires international coordination that goes beyond current arrangements. Data sharing agreements help with forecasting, but response coordination remains fragmented. Some countries have invested heavily in grid hardening while others lag behind. Standardized protection requirements could improve overall resilience but would require unprecedented cooperation. Looking ahead to the remainder of Solar Cycle 25, the November 2025 events serve as both warning and preview of what might come. If the Sun can produce such intense activity during what was predicted to be a moderate cycle, the approaching solar maximum could bring even more severe challenges. The question isn't whether another major space weather event will occur, the question is whether we'll use the time we have left to prepare adequately, or whether we'll learn the hard way that our technological civilization exists at the mercy of forces beyond our control. Beyond our control. The technological dependencies that make modern society vulnerable to space weather continue expanding at an exponential rate. Every smartphone contains GPS receivers that space weather can disrupt. Every credit card transaction relies on timing signals that solar storms can scramble. Every connected device from smart thermostats to industrial sensors assumes reliable electromagnetic environments that coronal mass ejections can shatter without warning. This interconnectedness creates cascade vulnerabilities that didn't exist even a decade ago. When GPS fails, it doesn't just affect navigation, it disrupts the timing synchronization that keeps cellular networks operational. It breaks the coordination between traffic lights that prevents gridlock. It disables the precision agriculture systems that modern farming depends on. A single space weather event can trigger failures across multiple sectors simultaneously. The November 2025 storms revealed how quickly these cascades can develop. Radio operators in Germany lost contact with emergency services. Air traffic controllers in France struggled with degraded radar systems. Power companies across Scandinavia reported transformer heating beyond safe operating limits. Each failure created stress on backup systems that weren't designed to handle the additional load. Consider the supply chain implications that most people never think about. Modern logistics depends on GPS tracking for every shipment. Warehouse robots navigate using satellite positioning. Inventory management systems assume constant connectivity to optimize stock levels. When space weather disrupts these systems, the effects ripple through the global economy in ways that compound over time. The pharmaceutical industry faces particular vulnerabilities because many medications require temperature-controlled storage and transport. Insulin spoils without refrigeration. Vaccines lose effectiveness if exposed to heat. Blood banks need reliable power for storage systems. During the November storm, several European medical facilities reported temporary cooling system failures that required emergency generator activation. Food distribution networks operate on razor-thin margins that assume predictable delivery schedules. Supermarkets typically maintain only 3 days of inventory. Restaurants receive daily shipments of fresh ingredients. Cold storage facilities need continuous power to prevent spoilage. A prolonged space weather event could trigger food shortages in urban areas faster than most people realize. The financial sector's vulnerability extends beyond high-frequency trading to basic banking operations. ATM networks depend on satellite communications in remote areas. Credit card authorization systems require precise timing coordination. International wire transfers assume reliable data connections between banks. The November events caused minor delays in some transactions, but a more severe storm could freeze financial networks entirely. Water treatment facilities increasingly rely on automated systems that space weather can disrupt. Chemical dosing requires computer-controlled precision to maintain safe drinking water. Pump coordination depends on communication networks between treatment plants. Billing and customer service systems need database connectivity. While water infrastructure includes more manual backups than power grids, extended disruptions could affect both quality and availability. Transportation networks face multi-layered vulnerabilities that go far beyond GPS navigation. Modern aircraft use satellite communications for oceanic flights, where ground-based radio coverage doesn't exist. Air traffic control systems require nanosecond timing synchronization between radar stations. Railway signaling increasingly uses electronic systems vulnerable to electromagnetic interference. The aviation industry has developed protocols for managing space weather risks, but implementation varies between carriers and regions. Some airlines proactively reroute polar flights when solar activity increases. Others wait for official warnings before adjusting operations. The economic pressure to maintain schedules conflicts with safety considerations when radiation levels spike during solar storms. Commercial shipping faces similar challenges on a global scale. Container ships use GPS for navigation and satellite communications for weather updates. Port operations depend on automated crane systems that electromagnetic interference can disrupt. Just-in-time delivery schedules assume predictable arrival times that space weather can scramble. The military implications of space weather extend beyond communication disruptions to fundamental questions of national security. Modern warfare depends on satellite reconnaissance that solar storms can blind. GPS-guided weapons become unreliable when timing signals degrade. Networked command systems fragment when electromagnetic conditions prevent reliable data transmission. International tensions could escalate rapidly during space weather events as normal diplomatic channels fail and military surveillance capabilities degrade. Communication satellites that enable crisis management could be damaged or disrupted exactly when they're needed most. The fog of war thickens considerably when electromagnetic storms disable the sensors and networks that modern militaries depend on. Space weather also affects the rapidly growing commercial space industry in ways that cascade back to Earth-based services. Satellite internet constellations provide backup connectivity for remote regions. Launch schedules depend on space weather forecasts for crew safety. Manufacturing experiments in orbit require stable electromagnetic environments. The psychological dimension of space weather preparedness remains largely unexplored by emergency management agencies. Most people have never experienced a prolonged power outage or communication blackout. The skills needed for self-sufficiency during extended outages have atrophied in urban populations accustomed to constant connectivity and reliable services. Community resilience varies dramatically based on social cohesion and local preparedness levels. Neighbourhoods with strong social networks and established emergency plans perform better during disasters. Areas with high trust levels see more cooperation and less panic when infrastructure fails. But space weather events affect large regions simultaneously, potentially overwhelming even well-prepared communities. The November storms demonstrated how quickly misinformation spreads when normal communication channels become unreliable. Social media posts claiming alien attacks or government conspiracies gained traction as official information sources struggled with connectivity issues. Emergency management agencies found it difficult to correct false information when their own communication systems were degraded. This information chaos represents another hidden vulnerability of modern society. People accustomed to instant access to news and expert analysis become anxious and prone to panic when those information sources suddenly disappear. The psychological stress of technological isolation can trigger irrational behavior that compounds the practical challenges of infrastructure recovery. Healthcare systems face cascading vulnerabilities that extend far beyond backup power for critical equipment. Electronic medical records become inaccessible when network connections fail. Prescription systems can't verify medication histories or drug interactions. Telemedicine services that rural areas depend on become unavailable when satellite links degrade. The aging population in developed countries increases vulnerability to extended power outages. Elderly residents depend on air conditioning during heat waves and heating during winter storms. Medical devices from oxygen concentrators to dialysis machines require reliable electricity. Medication that needs refrigeration spoils without consistent power. Emergency medical services struggle when multiple systems fail simultaneously. GPS navigation becomes unreliable for ambulance dispatch. Radio communications degrade when ionospheric conditions change. Hospital networks lose connectivity with emergency responders. The coordination that modern emergency medicine depends on breaks down exactly when it's needed most. Educational institutions carry hidden vulnerabilities that could disrupt learning for millions of students. Online learning platforms depend on satellite internet in rural areas. Student information systems require reliable database connections. Even basic classroom technologies like interactive whiteboards need network connectivity to function properly. The economic implications of extended educational disruptions ripple through society in ways that compound over time. Parents can't work when schools close unexpectedly. Online learning inequalities become more pronounced when connectivity is unreliable. Standardized testing schedules get disrupted when computer systems fail. Manufacturing systems increasingly depend on just-in-time coordination that space weather can scramble. Automated production lines assume reliable communication with suppliers. Quality control systems need constant data connections to maintain standards. Inventory management depends on GPS tracking for raw materials and finished products. The automotive industry faces particular challenges as vehicles become more computerized and connected. Modern cars contain dozens of electronic systems that electromagnetic interference can affect. GPS navigation fails when satellite signals degrade. Wireless connectivity for software updates becomes unreliable during solar storms. Electric vehicle charging networks represent a new vulnerability that didn't exist during previous solar cycles. Charging stations need reliable power grid connections and communication networks for payment processing. Smart grid coordination assumes constant data exchange between utilities and charging infrastructure. A severe space weather event could strand electric vehicle owners without access to charging. The renewable energy sector faces unique space weather challenges that traditional power generation doesn't experience. Solar panel efficiency can be affected by increased atmospheric absorption during geomagnetic storms. Wind turbine control systems depend on GPS timing for grid synchronization. Energy storage systems require sophisticated electronics vulnerable to electromagnetic interference. Smart city initiatives create new pathways for space weather impacts to propagate through urban infrastructure. Traffic management systems assume reliable sensor networks and communication links. Waste management depends on GPS tracking for collection routes. Public transportation uses automated systems for scheduling and fare collection. The Internet of Things revolution multiplies potential failure points during space weather events. Smart home devices lose connectivity when communication networks degrade. Industrial sensors can't report equipment status when electromagnetic interference increases. Agricultural monitoring systems fail when satellite links become unreliable. Cybersecurity challenges multiply during space weather events as normal monitoring and response capabilities degrade. Network security systems may miss intrusions when communication channels are unreliable. Backup systems designed for terrestrial threats may not account for space weather vulnerabilities. The chaos of infrastructure failures creates opportunities for malicious actors to exploit compromised systems. Financial market volatility could spike during space weather events as automated trading systems malfunction and communication between markets becomes unreliable. High-frequency trading algorithms depend on microsecond timing that GPS disruptions can scramble. Market data feeds can become corrupted when satellite links degrade. The psychological impact of technological uncertainty could trigger selling panics. Insurance companies are beginning to recognize space weather as a significant risk factor, but coverage remains inconsistent across sectors and regions. Some policies explicitly exclude space weather damage. Others offer specialized protection at premium prices. The industry's capacity to handle claims from a truly severe event remains questionable, given the potential scale of simultaneous failures. Corporate business continuity planning varies widely in how thoroughly it addresses space weather scenarios. Technology companies tend to have more robust backup systems and disaster recovery procedures. Manufacturing firms may lack adequate protection for automated production lines. Service industries often assume that communication networks will remain operational during emergencies. The human factor in space weather response deserves more attention than emergency planning typically provides. Operators managing critical systems during storms face information overload and high stress levels. Decision-making quality degrades when multiple alarms sound simultaneously. Training for space weather scenarios remains limited compared to other emergency types. Research into space weather impacts continues advancing, but significant gaps remain in understanding how modern interconnected systems respond to electromagnetic disturbances. Computer models can simulate individual system failures, but struggle with the complex interactions between multiple infrastructure networks. Real-world testing of space weather protection measures is expensive and logistically challenging. The November 2025 events highlighted the need for better coordination between government agencies, private companies, and international organizations during space weather emergencies. Information sharing protocols worked reasonably well for issuing warnings, but response coordination revealed gaps in authority and responsibility during actual infrastructure impacts. Climate change adds another layer of complexity to space weather risk assessment. Upper atmospheric heating during geomagnetic storms affects satellite, operations, and radio propagation. Changes in global circulation patterns may alter how space weather impacts propagate through different regions. The increasing frequency of extreme weather on Earth's surface could coincide with space weather events to create compound disasters. The workforce challenges in critical infrastructure sectors compound space weather vulnerabilities as experienced operators retire and younger engineers lack hands-on experience with manual backup procedures. Knowledge transfer becomes crucial when automated systems fail and human intervention is required. Training programs need to balance modern technology skills with traditional manual operation techniques. Public education about space weather risks remains minimal despite the growing vulnerability of modern society. Most people have never heard of coronal mass ejections or geomagnetic storms. Emergency preparedness recommendations rarely consider extended power outages lasting weeks or months. Community resilience programs focus on traditional natural disasters rather than electromagnetic threats. The global nature of space weather requires international cooperation that extends beyond current scientific collaboration. Response coordination during actual events needs predetermined protocols and clear authority structures. Standardized protection requirements could improve overall resilience but would require unprecedented international agreement on technical standards. Looking toward the peak of solar cycle 25, the lessons from November 2025 take on increasing urgency. The Sun's activity continues building toward maximum intensity expected sometime in late 2025 or early 2026. Active regions more complex than AR 4274 will likely emerge. The probability of multiple severe events occurring in rapid succession increases as the solar maximum approaches. The technological infrastructure that society depends on continues expanding and becoming more interconnected, even as space weather risks intensify. Smart city initiatives create new vulnerabilities. Autonomous vehicle networks assume reliable GPS signals. Artificial intelligence systems require massive computing resources vulnerable to power disruptions. The economic costs of space weather protection pale in comparison to potential damage from a severe event, but the mismatch between investment timescales and political decision-making cycles prevents adequate preparation. Utilities focus on quarterly earnings rather than decade-scale risks. Politicians respond to immediate crises rather than future threats. The result is systematic underinvestment in resilience measures. The November storm served as a stress test that revealed both strengths and weaknesses in our space weather preparedness. Early warning systems functioned well. International cooperation enabled effective monitoring and forecasting. But response coordination revealed gaps when multiple systems failed simultaneously. The interconnected nature of modern infrastructure amplified relatively modest space weather impacts in ways that previewed much larger potential disruptions. Time is running short for implementing the protection measures that could prevent a Carrington-level event from causing catastrophic damage to modern civilization. Every month of delay leaves critical infrastructure more vulnerable as technology becomes more sophisticated and interconnected. The sun won't wait for us to get ready. The countdown to solar maximum accelerates with each passing day, and the infrastructure we've built our civilization upon grows more fragile by the hour. What happened in November 2025 wasn't an anomaly. It was a preview of what's coming when solar cycle 25 reaches its peak intensity sometime in the next 12 to 18 months. Active region 4274 that produced those 3 devastating X-class flares has rotated off the visible solar disk, but it's being replaced by new magnetic complexes that show even more ominous characteristics. Solar physicists monitoring the sun's far side using helioseismic imaging have detected at least 4 large active regions forming in areas we can't yet observe directly. When these regions rotate into view over the coming weeks, they could dwarf the energy release we witnessed in November. The magnetic field measurements from these emerging regions suggest configurations that solar physicists describe with words like unprecedented and concerning. Beta-gamma-delta classifications that indicate twisted field lines storing enormous amounts of energy. These are the magnetic powder kegs that produce the most violent solar eruptions, and there are multiple regions developing simultaneously across the sun's surface. But here's what makes this situation particularly dangerous. The November storms occurred when Earth's magnetosphere was in a relatively stable configuration. The interplanetary magnetic field orientation was moderately favourable for deflecting some of the incoming energy. The timing allowed power grid operators to implement protective measures before the worst impacts arrived. Next time, we might not be so fortunate. Magnetospheric physics tells us that small changes in the orientation of magnetic fields embedded in solar wind can dramatically alter how much energy gets transferred to Earth's magnetic environment. If the next major coronal mass ejection arrives with a southward-pointing magnetic field, something that happens roughly half the time, the coupling efficiency increases by factors of 10 or more. The same solar eruption that caused G4 conditions in November could produce G5 extreme storm levels under different magnetic orientations. G5 storms represent the threshold where widespread voltage control problems begin cascading into complete system collapse. Historical G5 events have caused continent-wide power outages, destroyed hundreds of transformers simultaneously, and triggered economic disruptions measured in the hundreds of billions of dollars. The Halloween storms of 2003 knocked out power across Sweden and damaged transformers from New Jersey to South Africa. The March 1989 storm blacked out Quebec for 9 hours and nearly collapsed the entire North American power grid. Those events occurred when our technological infrastructure was far less sophisticated and interconnected than it is today. The internet was in its infancy. GPS had limited civilian applications. Satellite constellations consisted of dozens of spacecraft, not thousands. The vulnerabilities have multiplied exponentially while our protection measures have advanced only incrementally. The satellite industry provides a stark example of how our exposure has grown. In 1989, fewer than 200 active satellites orbited Earth. Today, that number exceeds 8,000 and continues climbing rapidly as companies launch massive constellations for global internet coverage. Each satellite represents millions of dollars in investment and provides services that millions of people depend on daily. A severe space weather event could damage or destroy hundreds of these satellites simultaneously. SpaceX's experience in February 2022 offers a preview of what's possible. A relatively minor G1 geomagnetic storm increased atmospheric drag enough to prevent 40 newly launched Starlink satellites from reaching operational altitude. They re-entered Earth's atmosphere and burned up, representing a loss of tens of millions of dollars from a minor space weather event. Imagine the losses during a G5 storm that could affect satellites across multiple orbital altitudes. The commercial space industry has grown into a multi-hundred billion-dollar sector that underpins critical services from GPS navigation to weather forecasting to international communications. This infrastructure exists in an environment where space weather can destroy investments worth billions in a matter of hours. Yet most space companies continue operating with minimal protection against electromagnetic threats that are not just possible, but inevitable. Insurance companies are beginning to recognize the scale of potential losses. Lloyd's of London issued warnings that space weather could trigger insurance claims exceeding the industry's capacity to pay. Some insurers now exclude space weather coverage from satellite policies. Others charge premiums that reflect the growing risk as solar activity increases toward maximum. The market is pricing in dangers that government agencies and the public still largely ignore. The telecommunications industry faces similar exposure multiplication. Cell towers that once operated independently now form integrated networks where failures cascade across wide areas. Fiber optic cables carry vastly more traffic than the copper wires they replaced, making each failure more disruptive. The migration to 5G technology creates new vulnerabilities as networks become more complex and interdependent. Internet traffic has grown by orders of magnitude since the last solar maximum in 2014. Streaming video, cloud computing, and remote work have made constant connectivity essential for economic activity. A space weather event that disrupts internet infrastructure for days or weeks would trigger economic losses that dwarf the direct costs of damaged equipment. The financial sector's dependence on electronic systems has reached levels that would have seemed impossible during previous solar cycles. High-frequency trading now accounts for more than half of all stock transactions, operating on microsecond timing that GPS disruptions can scramble. Cryptocurrency mining consumes enormous amounts of electricity and computing power that space weather can interrupt without warning. Digital payment systems have largely replaced cash transactions, creating single points of failure that didn't exist when most commerce was conducted with physical currency. Consider what happens when electronic payment systems fail during a space weather event. Credit card transactions stop processing, ATM networks go offline, mobile payment applications lose connectivity, online banking becomes inaccessible. The cashless society that we've been building assumes constant electronic connectivity that solar storms can sever in minutes. The healthcare system's vulnerability has grown exponentially as medical devices become more sophisticated and interconnected. Electronic health records require constant database connectivity. Prescription systems verify medication interactions through online databases. Medical imaging equipment depends on network connections for storing and transmitting diagnostic images. Telemedicine services that rural areas depend on become unavailable when satellite communications fail. Modern hospitals operate more like technology centers than the mechanical institutions of previous decades. Patient monitoring systems generate continuous data streams. Automated drug dispensing systems require network connectivity for safety verification. Even basic functions like scheduling and billing depend on electronic systems that space weather can disrupt. The November storms caused minor glitches in some medical systems across Europe and Africa. Heart monitors lost connectivity with central nursing stations for brief periods. Prescription verification systems experienced delays. These were temporary inconveniences during a moderate space weather event. During a severe storm, such disruptions could become life-threatening emergencies. Emergency response systems that society depends on during disasters face cascading failures when space weather disrupts the communication networks they require. First responders rely on radio systems that ionospheric disturbances can render useless. Emergency dispatch centers depend on GPS coordinates that become unreliable when satellite signals degrade. Hospital networks lose connectivity with ambulance services exactly when coordination becomes most critical. The November events provided glimpses of these vulnerabilities. Radio operators across Europe reported complete loss of high-frequency communications during peak storm conditions. Emergency services in Germany struggled with degraded radio coverage. Air traffic controllers in France dealt with radar systems that became unreliable when ionospheric conditions changed rapidly. These weren't catastrophic failures because backup systems functioned and the storms didn't last long enough to exhaust emergency power supplies, but they demonstrated how quickly the coordination systems that modern emergency response depends on can degrade when electromagnetic conditions change. Urban areas concentrate both the highest population densities and the most vulnerable technological systems. Skyscrapers depend on elevator systems that power outages disable. Subway networks require constant electrical power for ventilation and safety systems. Traffic management relies on electronic signals and communication networks that space weather can disrupt simultaneously. The heat island effect makes cities particularly vulnerable to extended power outages during extreme weather. Concrete and asphalt store solar energy during the day and release it at night, keeping urban temperatures elevated. Air conditioning demand remains high even after sunset during heat waves. If space weather damaged transformers during a summer heat dome, restoring power would become a race against time to prevent heat-related casualties. Water treatment and distribution systems increasingly depend on automated controls and communication networks that space weather can interrupt. Chemical dosing requires computer-controlled precision to maintain safe drinking water quality. Pump coordination depends on communication links between treatment facilities. Billing and customer service systems need database connectivity that electromagnetic storms can sever. While water infrastructure includes more manual backup systems than power grids, extended space weather disruptions could affect both water quality and availability in urban areas. The November storms caused temporary communication failures at several water treatment plants in Europe, though backup systems prevented service interruptions. Transportation networks face multi-layered vulnerabilities that extend far beyond GPS navigation failures. Commercial aviation depends on satellite communications for oceanic flights, where ground-based radio coverage doesn't exist. Air traffic control systems require nanosecond timing synchronization between radar stations that space weather can disrupt. Railway signaling increasingly uses electronic systems vulnerable to electromagnetic interference. The shipping industry moves the majority of global trade through container ships that use GPS for navigation and satellite communications for weather updates and route optimization. Port operations depend on automated crane systems and inventory tracking that electromagnetic interference can scramble. Just-in-time delivery schedules assume predictable arrival times that space weather can disrupt across multiple transportation modes simultaneously. Supply chain disruptions from space weather could propagate through the global economy for months after the original electromagnetic disturbance ends. Modern logistics operates on mathematical optimization that assumes reliable communication and timing systems. When those assumptions break down, the efficiency gains from globalization reverse into vulnerabilities that compound over time. The November storms caused minor delays in shipping schedules and temporary communication blackouts for some vessels in the North Atlantic. These were manageable disruptions during a moderate space weather event. A severe storm could trigger supply chain chaos that makes recent pandemic-related shortages seem minor by comparison. Manufacturing systems have become increasingly automated and interconnected in ways that create new pathways for space weather disruption. Assembly lines depend on just-in-time coordination with suppliers through communication networks that electromagnetic storms can interrupt. Quality control systems need constant data connections to maintain production standards. Inventory management relies on GPS tracking for raw materials and finished products. The automotive industry exemplifies how manufacturing vulnerability has grown. Modern vehicles contain dozens of electronic systems that must be precisely calibrated and tested during production. Assembly plants coordinate with suppliers across multiple time zones through satellite communications. Quality control data flows through networks that space weather can disrupt at critical moments in the production process. Electric vehicle manufacturing adds new vulnerabilities that didn't exist during previous solar cycles. Battery systems require sophisticated testing equipment, vulnerable to electromagnetic interference. Charging infrastructure depends on smart grid coordination that assumes constant data exchange between utilities and manufacturers. Software updates for vehicle systems rely on satellite connectivity that solar storms can interrupt. The renewable energy sector faces unique space weather challenges that traditional fossil fuel generation doesn't encounter. Solar panel efficiency can be temporarily reduced by increased atmospheric absorption during geomagnetic storms. Wind turbine control systems depend on GPS timing for grid synchronization. Energy storage systems require sophisticated electronics that electromagnetic pulses can damage or disrupt. Smart grid initiatives create new pathways for space weather impacts to propagate through electrical infrastructure. Advanced metering systems depend on communication networks that solar storms can interrupt. Demand response programs assume reliable data exchange between utilities and customers. Grid optimization algorithms require real-time information that space weather can corrupt or delay. The Internet of Things revolution has multiplied potential failure points exponentially. Smart home devices lose functionality when communication networks degrade. Industrial sensors can't report equipment status when electromagnetic interference increases. Agricultural monitoring systems fail when satellite links become unreliable during space weather events. Each connected device represents a potential failure point that didn't exist during previous solar maxima. The cumulative effect creates systemic vulnerabilities that are difficult to model or predict. A space weather event that causes minor disruptions to individual systems could trigger cascading failures across interconnected networks. Cybersecurity challenges multiply during space weather events as normal monitoring and response capabilities become degraded. Network security systems may miss intrusions when communication channels are unreliable. Backup systems designed for terrestrial threats may not account for space weather vulnerabilities. The chaos of infrastructure failures creates opportunities for malicious actors to exploit compromised systems. The convergence of space weather and cyber threats represents a particularly dangerous scenario that security analysts are only beginning to understand. A coordinated cyber attack timed to coincide with a major geomagnetic storm could overwhelm response capabilities and cause damage that exceeds the sum of both threats individually. Financial markets could experience unprecedented volatility during severe space weather events as automated trading systems malfunction and communication between markets becomes unreliable. High-frequency trading algorithms depend on microsecond timing that GPS disruptions can scramble. Market data feeds become corrupted when satellite links degrade. The psychological impact of technological uncertainty could trigger panic selling that traditional circuit breakers might not contain. The integration of artificial intelligence into financial systems creates new vulnerabilities that didn't exist during previous solar cycles. Machine learning algorithms assume constant data feeds that space weather can interrupt. Automated decision-making systems may not recognize space weather as a legitimate cause of system failures. The speed at which AI systems operate could amplify market disruptions before human oversight can intervene. Corporate business continuity planning varies widely in how thoroughly it addresses space weather scenarios. Technology companies tend to have more robust backup systems and disaster recovery procedures developed for terrestrial threats. Manufacturing firms may lack adequate protection for automated production lines that space weather can disrupt. Service industries often assume that communication networks will remain operational during electromagnetic emergencies. The human factor in space weather response remains inadequately addressed by most emergency planning. Operators managing critical systems during storms face information overload and decision fatigue when multiple alarms activate simultaneously. Training for space weather scenarios remains limited compared to other emergency types. The November events revealed cases where human error compounded technical failures during electromagnetic disturbances. Research into space weather impacts continues advancing, but significant gaps remain in understanding how modern interconnected systems respond to electromagnetic disturbances. Computer models can simulate individual system failures, but struggle with the complex interactions between multiple infrastructure networks during severe space weather events. Climate change interactions with space weather add complexity to risk assessment that scientists are only beginning to understand. Upper atmospheric heating during geomagnetic storms affects satellite drag and radio propagation in ways that may be changing as global circulation patterns shift. The increasing frequency of extreme weather on Earth's surface could coincide with space weather disruptions to create compound disasters that exceed response capabilities. The November 2025 events demonstrated that our space weather forecasting capabilities, while impressive, still can't provide the strategic warning that infrastructure protection requires. We can detect solar flares within minutes and track coronal mass ejections as they propagate through space, but we can't predict when specific active regions will erupt or how powerful those eruptions will be. This forecasting gap creates a fundamental challenge for infrastructure protection. Utilities can respond to storm warnings by monitoring transformer temperatures and adjusting grid operations, but they can't plan maintenance schedules or spare parts inventory based on accurate long-term space weather predictions. The result is reactive rather than proactive risk management. International cooperation on space weather monitoring has improved significantly, but response coordination during actual events reveals gaps in authority and responsibility. Information sharing protocols work well for issuing scientific warnings, but operational coordination between government agencies, private companies, and international organizations needs strengthening before the next major event occurs. The global nature of space weather means that impacts in one region can propagate through interconnected systems to affect areas that experience no direct electromagnetic disturbance. Financial networks, communication systems, and supply chains create pathways for space weather effects to spread far beyond the geographic areas where satellites and power grids experience direct damage. Looking toward the approaching solar maximum, every indicator suggests that more severe space weather lies ahead. Solar cycle 25 continues exceeding early predictions for intensity and duration. The magnetic complexity of emerging active regions appears greater than typical for this phase of the solar cycle. Multiple large active regions are developing simultaneously, increasing the probability of major eruptions occurring in rapid succession. The technological infrastructure that civilization depends on continues expanding and becoming more vulnerable, even as space weather risks intensify. Autonomous vehicle networks assume reliable GPS signals. Smart city initiatives create interconnected systems with multiple failure points. Artificial intelligence applications require massive computing resources that power disruptions can disable without warning. Economic incentives remain misaligned with space weather risks because the threats operate on timescales that exceed typical business and political planning horizons. Companies focus on quarterly earnings rather than decade-scale electromagnetic risks. Politicians respond to immediate crises rather than invisible future threats. The result is systematic underinvestment in protection measures that could prevent catastrophic damage. The insurance industry's evolving recognition of space weather risks reflects growing awareness of potential losses, but coverage remains inconsistent and may prove inadequate during a truly severe event. Some policies explicitly exclude space weather damage, while others offer specialized protection at premium prices. The industry's capacity to handle simultaneous claims from multiple sectors during a major electromagnetic storm remains questionable. Time is running out for implementing the infrastructure hardening that could prevent a Carrington-level space weather event from causing civilization-altering damage. Every month of delay leaves critical systems more vulnerable as technology becomes more sophisticated and interconnected. The lessons from November 2025 are clear, but translating those lessons into protective action requires overcoming institutional inertia and short-term thinking that pervades decision-making at every level. The Sun approaches its maximum activity phase with active regions more complex and energetic than models predicted. The infrastructure we've built assumes electromagnetic stability that space weather can shatter in minutes. The warning signs are flashing red, but most people remain unaware that our technological civilization exists at the mercy of a variable star that follows no human schedule and respects no political boundaries. Schedule and respects no political boundaries. The convergence of these vulnerabilities creates a perfect storm scenario that keeps risk analysts awake at night. We're not just talking about individual system failures anymore. We're talking about synchronized collapse across multiple critical sectors simultaneously. When your smartphone loses GPS, your car's navigation fails, the traffic lights go dark, and the power grid destabilizes all at once, you're not dealing with separate problems. You're witnessing the unraveling of interconnected systems that were never designed to fail together. The mathematics of cascading failures are brutally simple. Each system depends on others for proper operation. Power grids need communication networks for coordination. Communication networks need power for operation. Transportation systems need both power and communication. Financial networks need all three. When space weather attacks the electromagnetic foundation that everything else builds upon, the failures don't add up. They multiply. Emergency planners call this the bathtub curve of disaster response. Individual system failures can be managed with existing resources and procedures. But when multiple critical systems fail simultaneously, response capabilities get overwhelmed exponentially. The resources needed to manage 10 separate problems occurring at once aren't 10 times greater than managing one problem. They're 100 times greater, because each failure complicates the response to every other failure. The November storms offered a preview of this multiplication effect on a limited scale. Radio operators lost contact with emergency services, while power companies struggled with transformer overheating, while satellite operators dealt with radiation exposure. Each problem was manageable individually, but the simultaneous occurrence stretched response capabilities in ways that revealed dangerous gaps in coordination and resources. The sun has spoken. November 2025 wasn't just another month of solar activity. It was a warning shot across the bow of our technological civilization. While we debate whether an interstellar comet might have influenced our star, we're missing the bigger picture. Our infrastructure is failing the most basic stress tests that space weather can deliver. The next major solar storm isn't a question of if, but when. And when it arrives, it won't care about our political debates, our economic priorities, or our comfortable assumptions about technological reliability. The only question that matters now is whether we'll heed this warning, or learn the hard way that our entire way of life hangs by the slimmest of electromagnetic threads.